Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that so far we have been talking about utility functions in the context of portfolio management, and we identified that the eventual goal is to maximize the expected utility of an investor, and we started talking about the context of non-mean variance analysis. So, we will start in this today's lecture, we will start off with digging a little deeper into this notion of non-mean variance analysis. We will look at a particular example, and then we will talk about the first of the several criteria that can be used in the non-mean variance framework, namely the safety first criteria. So, we start the lecture. So, we make the statement that in the mean variance approach, the assumption is that the assets are normally distributed and that the investors have quadratic utility. Also, the assumption is that the two parameters, namely mean and variance, remember this is the mean variance framework, these are by themselves sufficient to describe the investment environment. So, accordingly, so once these circumstances do not hold, so that means in other circumstances that means when they are not normally distributed or when you do not have quadratic utility, those under circumstances a new set of portfolio selection criteria is needed. Now, some of these cases are, so these include, so for example, a geometric mean return, which we will discuss in today's class. Then we have the safety first criteria. The third is value at risk. This is something we will discuss in detail in the later half of the course, or VAR. Then we have something called the semi variance. You have stochastic dominance and something which is known as the mean variance skewness criteria. Okay, so just an observation that although some of these criteria may still only use mean and variance, they do not require any specific distribution. So, you could have a more generalized setup where you are not restricted only just to the assumption of normally distributed random variables. Okay, so let me start off with the first of this criteria, and this is what is known as the geometric mean return criteria. So, the geometric mean of historical returns, so we will denote this by RG for geometric mean, and the bar at the top for the mean is defined as RG bar is equal to 1 plus R1, that is the return for the first period, into 1 plus R2 return from the second period, into 1 plus RT return for the tth period raised to 1 by t minus 1. So, this can be written in the short form product of 1 plus RT, t is equal to 1 to capital T raised to 1 over t minus 1. So, this comes from the fact that if you have if you start off with an amount of say P naught, and then at the end of time period 1 it becomes goes by a factor of 1 plus R1, then 1 plus R2. So, at the end of time period t, I will have the product all the way to 1 plus RT, and this will be equal to P naught into 1 plus RG bar raised to t for t time periods. So, this is going to give you 1 plus RG bar is equal to 1 plus R1 into 1 plus R2 all the way to 1 plus RT raised to 1 over t, and this implies that RG bar is equal to 1 plus R1 into 1 plus R2 all the way to 1 plus RT raised to 1 over t minus 1. So, that is the derivation of this result here. Okay, in this setup, the assumption is that each of the observations is equally likely, that is equal to probability of 1 over t. Alternatively, when the probability of each return observation are not equal, but rather are denoted by Pi, then the geometric mean return is given by RG bar is equal to, so I will take a Q from this form. So, this is going to be product of j is equal to 1 to s into 1 plus R j raised to P j minus 1. So, here you observe that instead of t I have replaced it with s, and instead of I small t I have replaced this with j. So, basically I am considering s number of periods just to distinguish it from the notation for the notation I have here. And here of course, my 1 by t, this is being replaced by my P j, and your R t is replaced by R j. Okay, so now the next thing we need to do is look at what is the maximum maximization of the wealth at the terminal point, that is t. And so, accordingly what we will do is that we will get the formulation for W of t in the context of the geometric mean return, and then we will calculate what is going to be the expected final wealth. So, we start off with maximizing the terminal wealth. So, in the multi-period setting, it can be shown that the portfolio with the highest expected terminal value is the one with the highest expected GMR, that is geometric mean return. This can be observed by noting that W of t is going to be W naught into 1 plus R 1 into 1 plus R 2 all the way to 1 plus R t, and this is going to be W naught into 1 plus R g bar raised to t. So, this will imply that expected value of W t is going to be W naught into expected value of 1 plus R g bar raised to t. So, that means the maximization of this is equivalent to maximization of the GMR. Okay, so here we can state that since W naught and t are constants, it can be shown that maximizing E of W t, that is this term here, is equivalent to maximizing E of GMR. So, that means maximization of this. So, accordingly, the GMR criteria suggests that one should choose that portfolio at the beginning of each period such that the expected value of GMR is maximized, which in turn ensures that E of W t is maximized. Now, we consider the log utility in the paradigm of the GMR criteria. So, if the investor has logarithmic utility function, then expected utility of W t is going to be the expected utility of natural log of W t, which is W naught into 1 plus R 1 into 1 plus R 2 all the way to 1 plus R t. And this can be written as natural log of W naught plus expected value of natural log of 1 plus R 1 all the way to 1 plus R t, and this is natural log of W naught plus expected value of natural log of 1 plus R g bar raised to t. This finally reduces to natural log of W naught into expected value of natural log of 1 plus R g bar with this capital T outside. Now, since W naught and T are constants, therefore, maximizing the expected utility of the final wealth level is equivalent. So, this is a constant and T is constant. So, accordingly maximization of expected utility of the final wealth amounts to maximization of the expected value this. So, this is equivalent to maximizing the expected value of natural log of 1 plus R g bar. So, the portfolio that has the maximum value for the expected value of natural log of 1 plus the GMR will also have the maximum value for expected value of 1 plus R g bar raised to t, because this is essentially equivalent to this. So, thus the GMR criteria is also an expected utility based criteria if investors have log utility functions. Alright, so now we move on to, once that we are done with the GMR criteria and how we showed that in case the utility function is a log utility. So, under the circumstances the maximization of the expected utility of the final wealth level is equivalent to maximization of the expected GMR value. So, now once this is done, we move on to our next criteria, and this is what is known as the safety first criteria, and it is some sort of a conservative criteria, and we will look at 3 different safety criteria. So, let us now first begin with motivating why safety first criteria are used in the first place. So, accordingly, we start this discussion on the safety first criteria. So, the motivation is as follows, that the Markowitz framework, this relies on the assumption that investors choose from portfolios on the basis of a utility function defined in terms of mean and variance of portfolio returns. Given the arbitrary nature of utility functions, more objective criteria were explored, and one of this is the safety first criteria. Okay, so this safety first criteria is driven by the motivation that we are only concerned with the risk of failure in achieving a certain minimum target return, or the failure to meet some pre-specified safety margins. So, this risk, so please understand I am not talking about the criteria here, but I am identifying the risk. This risk is commonly expressed as the following, that so if you have the portfolio return given by RP and you are worried that this will be less than or equal to some minimum target or pre-specified return that you want, which is RL. So, you want to check that what is going to be the probability of RP being less than or equal to RL, and this is risk is commonly expressed as that this probability must be less than or equal to alpha. So, this means that if you start off with a portfolio of P and the return of the portfolio is given by RP and it is a random variable, and then you fix a minimum level of return that you want, that is some sort of a safety threshold which you denote by R of L, and you want to always stay above this R of L. So, that means from the point of view of your risk, you are worried about what are the events under which you have, what are the events for which you will have RP less than RL, and what is going to be the probability of that, just to get an indication of the percentage chances that you will not be able to meet your target return of RL. And you basically you are worried that you want this probability should be less than or equal to some level, say alpha, which you can choose maybe 0.05 or 0.1. If you choose to be 0.05, this means that you do not want the chance of missing your target of RL by more than 5%. So, here we have introduced certain notations. So, the first one is RP. So, this is nothing but the return on portfolio P. Your RL, which was your target return, this is your desired level of return below which the investor does not wish to fall. So, this is often referred to as the disaster level or safety threshold. And finally, alpha is going to be the acceptable limit, that means the maximum possible percentage chance that you are willing to accept on the probability of failing to reach the minimum acceptable rate of return RL. This criteria, that probability of RP less than or equal to RL, that is less than or equal to alpha, is a very generic criteria, and of course, you want ideally your alpha to be equal to 0, that there is no likelihood that you will miss your target, but since RP is a random variable, so that is not likely to happen. So, your eventual goal is to meet the target in a manner that the probability that you miss the target is as small as possible. Now, keeping this general requirement of this probability of RP less than or equal to RL being less than or equal to alpha, we will now enumerate and describe in detail 3 different such criteria. And in today's class, we will start off and describe the first of those safety criteria, which is known as the Roy's safety first criteria. So, accordingly, we start with Roy's safety first criteria. It is a fairly classical approach. In 1952, Roy developed a safety first criteria with the goal of minimizing the probability of earning a disaster level of return, or what is known as the safety threshold. So, the goal is to minimize this probability that your portfolio return is below the your safety threshold or the disaster level. Okay, now what does this criteria implies? So, this criteria implies that the investors choose their portfolio by minimizing the loss probability for a fixed safety threshold called the floor return. So, this is called the floor return is because this is the bare minimum return that the investor wants to achieve, and anything below this is not acceptable to the investor. So, accordingly, Roy's criteria, the Roy's criteria attempts to control risk for a fixed return. So, now let us look at a specific situation, that if the statistical distribution of returns can be characterized by the mean and variance. So, no other moments are required or parameters are required. Then Roy's safety first criteria can be analyzed in the paradigm of the mean variance framework. So, for the sake of brevity, we assume that returns are normally distributed. Just for a simplistic case, we assume that returns are normally distributed. Then the optimum portfolio is the one that has the smallest area of a left hand side tail of the normal distribution. So, in order to see this, we do a little calculation. So, what do you want? You essentially want to minimize this probability. So, probability of R p less than R L. Now, this is the same as, so we subtract the expected return of R p from both the sides and divide by sigma p. So, this probability of R p less than R L becomes the probability of this ratio R p minus E R p over sigma p being less than R L minus E R p over sigma p. Now, here I can define my R p minus E R p. Remember, this is the standardization. So, if your R p follows a normal distribution, then R p minus E R p over sigma p, this will follow a standard normal distribution. So, accordingly, this becomes the probability of Z being less than R L minus E R p over sigma p. So, thus the Roy's criteria of minimizing the probability that your R p is less than R L reduces, in the case of R p being normally distributed, to the problem of minimizing the probability of Z less than R L minus E R p over sigma p. All right. So, let us see this graphically. How is this going to look? So, I have this normal distribution. So, I have this here and this is 0, and on the x axis we have R L minus E R p over sigma p. So, this is my random variable. Now, here you see, so Z follows a standard normal random variate. So, accordingly, what you will have is that the probability that Z is less than R L minus E R p over sigma p, this probability is going to be this area. All right. So, this means that you want to minimize this condition, and you see that you have to look at the smallest area. So, the minimization of this condition here is equivalent to the smallest area that has been shaded. So, that is the graphical interpretation of the Roy's safety first criteria in case the returns of the portfolio are assumed to be normally distributed with a mean of ERP and variance of sigma RP. So, that means that in this context the goal is to settle for a portfolio. So, you could have a whole bunch of portfolios. For each of those portfolios you will have RL minus ERP over sigma p, which will essentially set the area under the shaded curve. So, the area which has been shaded here, and you want to find that amongst those which of the one is going to give you the smallest area that is actually shaded. All right. So, to be more explicit, we say that in the figure the shaded area under the standard normal distribution indicates the probability that the returns of a portfolio falls below the safety threshold level RL. So, the probability that a standard normal variable is less than RL minus ERP over sigma p can be easily calculated from the N01 distribution table. So, now we look at an example to illustrate the Roy's safety first criteria. So, we consider 4 portfolios which we will designate as A, B, C and D with the following expected return and standard deviation with along with the safety threshold RL being 3%. So, that means that you want to choose a portfolio which gives at least a 3% return. So, let us have these portfolios A, B, C and D. So, first of all, let us have the expected return denoted by E of RP. So, for portfolio say A, say it is 12%, for portfolio B it is 10%, for portfolio C it is 15% and for portfolio D it is 10%. Okay, so next we have is the standard deviation sigma p. So, for portfolio A this is 9%, portfolio B is 4%, portfolio C it is 10% and portfolio D it is 8%. Then what is going to be our RL minus ERP over sigma p? Remember RL is 3%. So, in the first case it is going to be 3% minus 12% over 9%. So, this becomes minus 1.00. In the second case it is going to be 3% minus 10% over 4%. So, this is going to be minus 1.75. Likewise, we will have minus 1.20 and in the last case we will have minus 0.875. So, now what is going to be the probability? So, we will now calculate what is the probability of Z being less than RL minus ERP over sigma p. So, what is the probability that Z is less than minus 1? This probability from the table turns out to be 0.1587. The probability that Z less than minus 1.75, obviously this is going to be minus 0.0401. As you can see, this is smaller than the first one because this minus 1.75 is to the left of minus 1.00. Then for minus 1.20, you will expect that it will lie between this and it turns out that this is 0.1151, and for the last case you will have this to be 0.1908. Okay, so now you remember that the Roy's safety criteria basically means that what is going to be the minimum of this probability, and the minimum for this probability is going to be this one. So, accordingly I can write that the return from portfolio B has the smallest probability of falling below RL equal to 3%. Consequently, it is the best choice amongst the 4 portfolios when Roy's SafetyFirst criteria is applied. Okay, so now let us look at another aspect of Roy's SafetyFirst criteria in the paradigm of the portfolio returns following normal distribution. So accordingly, we will have minimize the probability. So I start off from where I left off earlier, that the problem reduces to minimization of probability of ZP being less than RL minus ERP over sigma p, on the assumption that RP follows a normal distribution, and this is equal to minimize RL minus ERP over sigma p. Remember that here we had this RL minus ERP over sigma p, and we wanted to minimize the area under the curve. So, the minimization of the area under the curve which is shaded, that amounts to minimization of this quantity. Now, the minimization of this quantity is the same as maximization of the negative of it, that is ERP minus RL over sigma p. So, the Roy's SafetyFirst criteria then means that in case of the returns of the portfolio being normally distributed, reduces to minimization of the probability here, which is then equivalent to maximization of the expected return of the portfolio, that is the excess return over your safety threshold divided by sigma p. So, this means that thus the optimal portfolio is the one with the greatest ERP minus RL over sigma p. Okay, so I just want to make a note here that this kind of criteria is applicable to any statistical distribution as long as it is characterized by only 2 parameters, namely mean and variance, and that the normality assumption is not necessary. Okay, so I want to conclude with one last observation, considering a particular case of the safety threshold RL being replaced by the risk free rate RF, then the criteria becomes maximization of E of R p minus R L over sigma p. So, now the R L becomes R f, and what is this? This is equal to S p, where S p is the Sharpe ratio. So, this means that the maximization the Roy's criteria essentially then reduces in case of the safety threshold or R L being equal to the same as the risk free rate, it reduces to the problem of maximization of the Sharpe ratio. So, accordingly what you can write is that, so this gives that E of R p is equal to R f plus S p into sigma p. So, from this relation we will get this relation for E of R p and is equal to R f plus S p sigma p. So, what is this? So, this is a straight line in the sigma p E R p space with intercept R f and slope S p. Remember, this is in the sigma p E R p plane. So, S p is the slope and R f is the intercept. Thus, the optimum portfolio using the Roy's safety first criteria is the one that has the greatest slope of the straight line originating at R f and passing through the portfolio. All right. So, this brings us to the end of this class. So, just to do a recap, we are slowly moving towards our detailed analysis of the non-mean variance framework, and we began with a motivation of why we need a non-mean variance framework, and then we looked at the first of this non-mean variance criteria, that is the geometric mean return, and then we looked at how the maximization of the expected utility of the terminal wealth in case of the utility function being a log utility function amounts to the maximization of the GMR, that is a geometric mean return. And then we started talking about the safety first criteria, which is driven by the motivation of minimizing the probability or the percentage chance that the return of your portfolio will fall below a predefined safety threshold, which you denoted by R of L. And we will talk about several such safety first criteria, and in today's class we began with a discussion on the Roy's safety first criteria, which seeks to essentially minimize the probability of the return of your portfolio falling below the certain threshold. And through an illustration of an example of where the returns are normally distributed, we saw how this is accomplished, and then we looked at a graphical interpretation of this, and then we concluded by connecting this Roy's safety first criteria to the Sharpe ratio that we have already seen as a criteria for portfolio performance evaluation. So, in the next class we will continue our discussion and look at the other safety first criteria that have been developed over the period of time. So, this concludes our lecture for today. Thank you for watching.